I try to do this live demo. Normally it has worked for me a number of times, and I enjoy it because it makes my adrenaline level go high, really high. And maybe it works, maybe not. So anyway, who in the audience has used XDS? Oh, this was very different 5 years ago. Great. So I'll talk a little bit about XDS itself, the program, where it comes from and so on, then how to use it and what diagnostics you get, and finally finish showing this new XDS GUI thing, which is not as fancy as other GUIs, but I think it does a decent job. So for that I have here on this USB stick, I have some data sets and we'll look at those. So the XDS program package, so to say, was written by Wolfgang Kapsch. He is at the Max Planck Institute in Heidelberg. He's officially retired, but he enjoys a position where he can still keep working part-time, and he just likes to do research. I joined in 2007, so that's already 7 years ago, and so that's now a team of 2 people, one retired, one with other duties, but it's simply something that I enjoy a lot, and I do this as a hobby more or less. But on the other hand, this means there is not a big team, there is no company that makes money and can employ people, or so that it's just trying to make the best out of our time. Okay, so there's a Linux, or several Linux distributions, 64 and 32-bit, and also for the Mac. Every couple of months there's a new version with either only bug fixes or also sometimes new features, but the program is really in a rather robust state, so not a lot is being changed. So XDS is also the name of the main program that does most of the work from indexing or integrating to scaling. So most people have a hard time understanding that it also does the scaling. So people look at me, stare at me, what do we need? Scale pack or aimless or something? No, it's not like that. It's all in one program. So if you want, you can take the data directly out of XDS and solve your structure. But of course, you can go otherwise. Then, if you have several data sets that you processed with XDS, they all are scaled internally within XDS, but each file that comes out represents only one data set. Now, sometimes you want to merge them together or scale one versus the other, for example, in mad scaling, then you would use the XScale program. So it's a tiny program in comparison to XDS. It has only one task. You can also do zero-dose extrapolation, which sometimes gives spectacular results to compensate for radiation damage. And I suggest to try it if you have good data with high multiplicity but a weak enormous signal that may be affected by radiation damage. Then it's something to try, but it's not really a default. XDS-Conf is a program that serves to both other program systems, and it also does something similar to C-truncate or truncate, so it calculates from the intensities, it calculates amplitudes, and it does this in a slightly different way than truncate does it, so the results are a little bit different also. And there is a number of associated programs. XDS Viewer, that's an open source program that serves to inspect those two-dimensional images control diagnostics that XDS writes out. You can also use it to look at single data frames. It's not very fancy at all, but XDS Stat is additional statistics that may be useful. The binary can be downloaded. It's in the wiki that I'll be talking about in a second. And finally, there's this new program that I'll show to you in the end, the graphical user interface. It's also open source, by the way. You can download it from the SourceForge.net. So XDS is interface to beamline software. So a lot of beamline software already generates suitable XDS.imp. Now, what is that? XDS.imp is written in red letters here, and that indicates it's a file. The program names are in italics, and the file names are in red. I try to be consistent because otherwise it may be quite confusing. Okay, and this is the file that XDS needs to do its job. So it has a description of the experiment and also tells XDS what it should do. And XDS does not read the headers as other programs do. You have to provide XDS with the data that describe your experiment. And this is both good and bad. It is good because it makes XDS simpler. It's much easier to maintain something. It cannot break in this respect. It's also bad because it involves a little bit more effort on your side, because you have to tell the program this is the distance and this is wavelength and so on and so on. And most of the scripts that are mentioned here just supply or take this information from the header and write this XDS.imp for use of XDS. So fairly easy. My own script is also here. That's the lowest one, generate XDS.imp. It's a bash script, so if you have a new detector that you would like to try with XDS for XDS data processing, you just grab this bash script and see how I treat those other detectors, and then you add some lines to it. It's very easy to understand, even if you're not a programmer. Okay, if you want to use CCP4 programs, actually two ways of feeding the data from XDS to CCP4 programs. Pointless is one way. So Pointless has a mode where it just converts the scaled data from XDS into a multi-record MTZ file for use with Aimless. That is one mode of using Pointless, very nice. It can also take integrate, so the result of the integration, which is then not scaled. This also works. And Pointless can just read XDS ASCII.html, so the output file which has unmerged data in it, to suggest space codes, like Phil just explained an hour ago. And then in my view, the more normal way of proceeding is using XDSConf to get amplitudes and to finally write an MTZ file for use with CCP4 programs. So in principle, both things are equally, I think, work almost equally well. I have not really compared them, but I guess the differences are probably very minor. If you go the XDSConf way, then you have a choice between three different MTZ files, one having the anomalous signal represented as anomalous difference. The second, CCP4I, it's called. It has I plus, I minus, sig I plus, sig I minus, and this has amplitude. So F plus, F minus, so it's F plus, F minus, F minus. So depending on which downstream program you want to use, this can be chosen. Okay, so where do you get information about XDS? So the website, where you can also download the program and read the documentation. The wiki is mentioned here. It's established in 2008. There's a CCP4 bulletin board. There's a webinar that was, I think, recorded in 2010. It's already a little bit old, but it doesn't show the GUI, for example, but I think the information is still useful. Some papers called X-ray tutorial in the Journal of Applied Crystallography. And if everything else fails, please send me an email and I'll try to look at your data, but be prepared to share your raw data with me confidentially, of course. So the wiki that I just mentioned has information about in the form of articles, like the Wikipedia. It's the same software. So it has articles about optimization of data processing and some explanations, tips and tricks, special. And most recently, we added the project of the ACA 2014 data processing workshop, which took part a week or so ago. And so if you go to the wiki, to the quality control article, this has a link to ACA 2014, and that has links to articles that can be used as tutorials, for example, for data processing. These are supposedly difficult projects, so you can look up how we process those. So as this is a wiki, anybody can contribute, and you can get your own account and write your own articles or fix errors and so on. Same is true for the CCP4 wiki that I set up also in 2008. Actually, this is the other CCP4 wiki. The other is, this is the one that is meant for users to be read but also written, whereas the official CCP4 wiki is for the developers to document their software. I think it's fair to describe it like that. So, coming to XDS, just a few things that set it apart from other programs, or used to set it apart from other programs. So the three-dimensional profiles of reflections are represented internally in the program, not as two-dimensional slices, but essentially information from two-dimensional information that resides in our frames is stitched together to form a three-dimensional representation of each profile within the program. And that is possible because Wolfgang Krapsch came up with a very sophisticated geometrical transformation that results in the profiles being transformed in the ways that they look highly similar, maybe completely undistorted. And that is very useful because it gives highly accurate intensities in profile fitting. So smooth scaling is also explained in one of these papers. Other programs use this today as well. Zero-less extrapolation has already been explained to some extent, is available in Xscale. And it is fast, so the program uses multi-threading, so it can use all the cores in your workstation, and you can also use several workstations for one data set. So internally it cuts the data set into, let's say, 2 or 4, some number of pieces, as many as there are computers that should work on the data, and it shells out, it tells each computer what to do, and the computers do their work independently, and in the end things are joined together. So this is very important at beamlines where the data collection where data processing should be as fast as data collection. So as I said, to use XDS you need a single file called XDS.imp, which describes everything, and it has keywords in it and parameters like detector distance would count as a keyword, and it has a parameter ability because there's a large number of such keywords. So if you just want to have go and not read all the documentation, you just download this generate XDS.imp script and give it the name of the data set, the files of your frames, and it will normally generate the XDS.imp for you. This works for Pilatus, MAR CCD, MAR image plate, and Rigaku detectors mostly. I don't think anything else. So the normal detectors that you find at the synchronous beamlines are accepted by this script here. Then you run XDS or the parallel version. But usually you had to type this on the command line. Now the GUI takes away this task from you. So as an example for the input file, this is just for certain detector, the MAR CCD detector, and the name of the detector is written somewhere. It says CCD chess here, detector equals CCD chess, and some specification about the number of counts that the pixel can have. This of course also has information about the names of the frames, distance, wavelength, oscillation range, and so on and so on. Okay, so this is highly technical. If you want to read this, it's all documented. There are no hidden features in the program and no undocumented commands or so. So there is no fiddling beyond what is available in this script that I showed. So the principle of using XDS is fairly simple to understand. There's one job line, this keyword is job, and it has 7 parameters, and they represent the 7 stages of data processing. I'll explain in a second what they do. So the data reduction is divided up in a modular way, I would say, and the steps are independent from each other in the sense that each of them can be run separately, one after the other in different runs of XDS, but they have to be run in this order that is shown here. And each step writes files that the later steps then use. Okay, so if you find out that you would like to change some parameter of your input for integration, then you don't need to start from here and rerun all those steps. You just have to rerun the integrate and make the correct step in that case. That makes a lot of sense once you get used to this. Each of these tasks or jobs writes its own output file. It has the same name as the task itself, but with capital LT appended to it. So what do these jobs do, these tasks? So it's a short documentation here. So XY core has to do with geometrical corrections. Normally this is not so interesting. Init establishes those pixels, or tries to find those pixels where no reflections are. This is done for the first, normally for the first 5 degrees of data, and this list of pixels is simply only used for scaling frames relative to each other. So the scaling, the first scaling is done based on background counts only. And that already compensates for fluctuations in beam intensity. So, and also volume of crystal in the beam. So it's a first scaling procedure that is integrated into the integration procedure. Okay. Cold spot is then a spot finding routine. IDXref is the indexing routine, which in principle works similar to the ones that were explained, except that it does not work in reciprocal space. It does not do these Fourier transformations. Rather, it collects difference vectors after transforming them back into reciprocal. So it takes the positions from the detector, transforms them back into reciprocal space, and then calculates the difference vectors, and difference vectors between reciprocal space lattice points always have to be integral, so difference between 2 HKLs is also like an HKL itself, so it has 3 components, and they should be not half or 1/3, or so they should be just integers. So there's a lot of output from IDXref, and finally you get a list of possible point groups, just in the same way as you've seen for MOSFET, and also in the HKL. So there's a strategy step that's not required. DevPix has to do with shadow masking integration, and this is the most time-consuming step, because given the unit cell, the primitive P1 unit cell normally, all the known unit cell that you specify, this step goes through all the data that you collected, and it writes the integrator of HKL, which has the integrated intensities, and the control image frame CPF, where you can see the superposition of the actual last frame and the predicted reflections on that frame. And correct is the scaling step. It puts statistics and writes the final XDS ASCII by HKL and the number of other files. So this is all very nice in principle. So this summarizes or gives you the information about the data flow here. So each of the steps that I just explained writes its own output files, and those arrows go to those files, and those files are then read by downstream steps, and so that the information can be passed on to the downstream steps. You can either inspect the files, they are just ASCII files with an editor or so, or you can look at them with XDS Viewer or let's say ADXV or so. So finally, you arrive at the after scaling, you get XDS ASCII.html. Then you have a number of choices. You can either go directly to XDS conf, as I explained in the beginning, get your MTZ file, very easy. Or you feed it into xscale if you have more than one such XDS ASCII.html. Then you would normally go to xscale and put them together and get one file that is then converted by XDS conf. You can get statistics, look at them, and now I also put pointless and aimless here for those who prefer to use CCP4 programs for this task. If you go this route, so it's not complete, as I said, you can also go from integrator.html directly to pointers and then aimless, so maybe this arrow is really missing here. And you should be aware of the fact that these data are already scaled, and it's really a matter of discussion whether aimless should scale them again. I always feel uneasy about this, so I would prefer, or I would suggest that people switch off the scaling in aimless, so that can easily be done, and use the data as they come from XDS ASCII.html. Alternatively, you can even switch off the scaling in correct. You can make correct, write this file, but with unscaled intensities. In that case, of course, we should scale within aimless. Yeah? And I would be interested to hear what your experience is with that. Okay. So this is what this final output file looks like. It has a header documenting the geometry and cell parameters and everything of your experiment. So in principle, if you have this file, you know what has been done. And in the end, you get this list of reflections, HKL, intensity, standard deviation of intensity, X and Y position on the detector where it was found, the frame number, it can be between two frames, and other stuff that is not so important here. So lots of things can go wrong, and we've been talking about many of those. First, I also have to mention the beam center. Yeah, everybody has mentioned this, but it's here. So the rotation can be backwards. That is what Phil said. Click this, if the spin should be reversed. Yeah, there are other things that that really represent problems of the beamline, beam flicker vibrations. We've talked about this. Yeah. If I look close, twinning overlooked wrong space group, everything that can go wrong will go wrong eventually. And sometimes in phasing or refinement, you find that your normal signal is too weak, and then you might have to redo your experiment. But it's important to get the right diagnostics from data processing, and I've been talking about statistical indicators in the morning, and I would like to present one more important quantity. I consider this important, and those who use it also find it useful. And let's look at the error model in a little bit more detail. The error model is the model that tells or that serves to calculate the error, the final error of the merge intensities, or even of the individual intensities. So they are manipulated, so to say, by using the error model to make them agree better with reality. So if we look at our random error indicated by R, this would be approximately the square root of the intensity. In some ways, so the background is not given. So this is essentially what the integration calculates. This is all it can do. The systematic errors, as I explained in the morning, they are related by some constant, let's call it B, with the intensity. So in reality, we find deviations between symmetry-related reflections that are normally bigger than the random error would predict. So this is why we have to introduce the systematic error term into our error model. So now the new error that is calculated, and this is now called the error model, is this new error for each measurement is the square root of this term here, And this just has a multiplier for the random error and a multiplier which occurs here in this formula. And I think I got it wrong. This should be then, yeah, the B and the B here, they are not the same B. Sorry. Okay, but for every data set, correct fits just two constants A and B, and they are used in this formula to modify the old random sigmas here to give these new adjusted sigmas. And these adjusted sigmas are calculated in such a way that they predict more or less accurately, or at least on average, the existing deviations between symmetrically related reflections. Now, one consequence of this simple error model, and I realize that in Aimless, your error model is a little bit more sophisticated. It has one more term, but some people say this.
Still not right.
Some people also say this term is not required, and you can make much more sophisticated error models. But with this very simple error model, it is very easy to say if the random error vanishes, so in case of a very strong reflection, this would result in I over sigma of 1 over square root of A times B. So once you know what A and B is, and correct tells it to you, you can calculate this quantity. This quantity is the highest I over sigma that any reflection can have in your data set, given the existing systematic error. So in other words, this asymptotic I over sigma tells you something about your systematic error, and it's completely independent from any random error. The random error has dropped out of the equation completely. So even for a very weak crystal, you can come up with this quantity, and it still tells you what the systematic error in your experiment is. And it turns out that this is a very good indicator for the quality of, let's say, the overall experiment. And this quantity I over sigma asymptotic, abbreviated ISA, is a measure of systematic error that arises in your experiment from the combined effects of beamline, crystal, detector, and data processing. And so if the geometric parameterization of the experiment is right, then I over sigma asymptotic increases or is high. And if all the choices in data processing are made correctly, you get close to the maximum of I over sigma asymptotic. In addition, it tells you how good your beamline is, how good your detector is. So if you find a high value of I over sigma asymptotic, then you know that everything has worked out perfectly, and that means the systematic error level is really low. Whereas in some cases, you go to a beamline, you collect data, and you find I over sigma asymptotic is low, even though your crystals were good. And that means there's something wrong at the beamline, too much shutter jitter or beamline instability or whatever. And the beamline people nowadays, they also know this, and they listen very carefully if you complain about your data and tell them the I over sigma asymptotic is only 15 for all my good crystals, and then they start fixing the problems. At least that is my experience. Normally, if you can optimize I over sigma asymptotic, you also get a good, better data. So the precision of your merged data is better, particularly at high resolution. Okay, so I think I can finish the talk here at this point, and we'll switch to the XDS GUI. This is fairly simple, and as XDS is also meant to be simple, the GUI, so is the GUI. The maybe fancy feature is that it is user extensible or modifiable. So it's not just a fixed piece of software, but you can change it. And I'll show you the places where you can change things according to your preferences. And this provides you with the information that you get from on the console output of XDS during data processing, and it produces plots synchronously at the same time with the processing. It's also documented in the XDS Wiki, and you can download it from there. So some references, I think, yeah, I can send you the PDF from this talk if you like. Okay, so now we'll try to close this. Okay. I had to copy actually the data from this fat USB stick to the disk because I wanted to plug in the disk and the HDMI cable, but there was not enough space here. So, yeah, ignore. Okay. So we'll try to run it here. See my terminal. Where is it?
This is the other screen.
YouTube, maybe. So, okay, XDS GUI, very simple. We should always also be looking at the console because some things are just written to the console. For example, if I run pointless from the GUI, its output will still be written to the console. Okay, so now the idea is very simple, very similar to what you've seen for IMOS film, except that in IMOS film the steps were from top to bottom, and here they are from left to right. So you start in the projects tab, move to the frame tab. This gives you the XDS.INP. Then all the outputs from XDS will be shown in the tabs that are grayed out now. Then you have the Tools tab with user modifiable commands. You can run XDS start, XDS conf, and xscale. That's the whole idea. And okay, now let us create a data processing folder for this project. Okay, it's called XDS Shiva. Is that? Raise your hand, Shiva. Shivash. Can you say your name?
Civis.
S
H
I
V
V
E
E
S
yeah.
H.
Ah. Okay. XDS. Okay. So you want to have a new folder for each project. So in this case, so I created just in my home directory XDS_Shivish. Okay, so now let's see where your data are. I go to the frame tab, load, and now file system temp. So as I said, I just copy the data there, Shivish, here. Something here, CABP2 data etc. Oh, lots of data sets.
Take any folder from first to file. Yeah.
This one?
Yeah, anyone before new.
Okay. So, okay. Yeah, so 8 megabyte files and 100 something, 159, okay. Maybe we can deal with this. Okay, I just click one of them, so the one is given here, the first one, and now I can change contrast and brightness. This screen is not wide enough actually, yeah. I mean, the beamer doesn't give me more pixels, it seems. I can zoom, yeah, like this. I can also zoom with the little mouse button. And I have now this generate XDS.INP here. Let's see if it works. So click it. This now reads the header, okay? And gives us XDS.INP, which is here. Yeah, very easy, go back and forth. Now what I don't like here, so I have to do something manually. I have to mask the beamstop, as you see. And so the green circle represents the 50 angstrom resolution circle. So 50 angstrom is just the default, shown here in this green line has 50 to 0. 0 means the whole detector essentially, but it starts as 50. I could now say, okay, don't use 50, use 20 or so. Yeah, maybe I should do this. Just change the 50 into a 20 and go back to the frame. Yeah. So the tabs are simply connected with each other. If I change the number, it will change into this looks ultimately good. But if I'm not happy with the masking, I can also use an uncasted ellipse, as it's called, yeah, and that I just do it like that with my mouse. So put this red ellipse here, just 2 mouse clicks. I could also use let's say quadrilateral, so it's a 4-sided thing to mask this. Yeah. Okay, so if I do this, I get these lines here in XDS.imp. So it's just graphical interface, just creates these lines in XDS.imp. Very simple. And so I guess the resolution is not that great in this case. So what I see here is, well, here it's 3.5. Yeah, here on, this looks a little bit weird, like, do you guys see it? There's something here, I don't know what it is, but it's 3.5 angstrom approximately. I don't think that we will get much, anything beyond 3.5 or maybe. Okay. Just put 3 here, be generous in this stage. Sometimes there is information at higher resolution, maybe in a different orientation of the crystal. This is, of course, not clear at the beginning. Now I put the 3 here, it shows me the 3 angstrom circle. Now going back to the XDS.imp tab, I could just say save, and run XDS. Okay. So let's see. Now you see here in the console the log file, but at the same time the tabs are being filled. So XY core, this is the LP file, the log file of the XY core, the init step. Read all of these. Not very interesting. Coldspot is now running. Now, this is now also different from other programs. I prefer in XDS to use many frames for spot finding and indexing. It makes things more robust, the results are better. It can index on a single frame or on 2 frames 90 degrees apart, but the recommended way is to use the first part of the data set for indexing, and that gives the best results, I would say. That's just my recommendation. Now, if we go to the console, there's an error message here, and it says insufficient percentage, less than 50% of index reflection. This happens often if things are not optimal. This is clearly not an optimal data set, I would say. And let's go through this indexing here. So at the beginning, this just tells us what the program has understood of your data. It's just echoes the stuff that we told it. Then we see it could find 48,000 spots on those in the first half of the data set. So the data set has 159 frames, and half of these were used for spot finding. That means from 1 through 79. So, and 41,000 out of these 48,000 are strong enough to be used for indexing. The cell parameters, so the reciprocal cell parameters are given here, 130, 169 angstrom, and the difference vectors are also shown here. They should be integral, right? And actually they are integral, or at least close to integral. If you see here something like 0.37 or so, then something is wrong, but in this case it looks quite good. So only 5 minutes, okay. So the angles are also given here. Cell parameters and angles are given here. Suspiciously close to 90 degrees, but not really 90 degrees. The population, that is something very important. We have the program tells you for the 3,000 strongest spots how many lattices it finds to explain these 3,000 spots. And it always gives you the 10 strongest lattices, and the first lattice has explains 2,676 out of these 3,000. So that's clearly a single lattice. It's not split or so. The problem now is we don't. If we go back here, maybe the beam position is not quite right. could be, I mean, the cross is where the header says the beam position is, but maybe not too far away. According to the header, this is the beam position, and the program refines for the given beam position, it refines the origin of this it refines the position where the 0, 0, 0 reflection would be, and it already tells us for the normal solution it's 1022, 1043, so it finds it 20 pixels away from there. That's it's a lot, I would say. It's not perfect, sorry, but so I don't see anything wrong with this at the moment. So I have no good idea why this is not a good indexing, and it finally, out of those 41,000, it can only index 9,000 or something. But using those 9,000 something spots, those 9,000 something spots can be predicted within 2 pixels and 0.8 degrees, which is not great. And now we get some information about possible lattices. That's very similar to what you have seen earlier. And in this case, it seems to be, or it could be an orthorhombic lattice with these unit cell constants. But at this stage, it looks like, it's difficult to say whether this is right, whether this is really orthorhombic. I mean, the third angle is 1.4 degrees away from 90 degrees, so that does not look optimal. So normally what I would do in this case is integrate in P1 and see what that gives us. So I can just continue. I would remove those first steps that have run nicely. We have some solution, and we will integrate it in P1. And now it's running. So the integrate step is running now, and during the integrate you already get here the plots. Yeah? So whenever it has finished a batch of data, the plots are updated. So you see the beam divergence for each frame, and then for each batch of data, mosaicity wiggling around let's say 0.8 degrees, so it's high mosaicity. This frame-to-frame scale factor, cell parameters, and some refinement results. The crystal detector distance is refined by default, and the crystal rotation is also being refined. Now it's only 159 frames, so it should be done by now. It goes automatically to the correct step, and it's at the moment it's scaling and trying to come up with a space group, but I guess we cannot be happy about what it comes up here. So I can lower the size here to make it fit on the screen. So ultimately, this tries to find out the space group also, and in different lattices it tries to scale the data, and as it seems, it looks like P1 gives the best RMEs for these data. So at the moment it seems to be more like the P1 crystal, and it should be reintegrated in P1 using the geometry that it found in this step. Just since we're at the end here now of our time, so down here you see the R values, R factor as a function of resolution, projections, completeness of the data. These are the curves. The different colors correspond to 9 different resolution ranges. I over sigma plotted, RME is plotted, CC1/2 is plotted for the different resolution range. The anomalous correlation and sig ano. So we get all the indicators in the plot, first as a function of resolution, and then down there as a function of data range. And then, in this case, it's we have to work more on these data. We can move to the Tools tab. Here we have Show Frame with Predictive Spots. For example, frame 1 would predict this, and hopefully zoom in. Make this right. So our indexing was, doesn't look too bad, but probably we have split reflections here. This doesn't look good to me, but overall, it may or may not be right here. Oh, okay, up here this looks pretty terrible. So I think this crystal is really wacky and questionable whether a lot can be squeezed out of this. But as Diederichs has already said, sometimes you can be very surprised of what you can squeeze out of a bad crystal. And okay, just a minute. Okay, saving good. So this is just to explain this. We have these 4 items here. One of them, for example, further analysis is it has the bash commands down here and the button for running pointless. So now pointless runs and the output is shown here in this console. And if you like, you can change the command just by your editing here this line. It's editable, and if you go out of XDS GUI, it will be saved in your home directory. There's a file .xds GUI, and your changes will be stored there. And here you could have your own commands. You could run HKL to map as a user-defined command. You can change the label on the button and so on. And all the other things that are already prepared for you to use, they are, you can change them just by changing these little bash commands here. They do those things that you would normally do on the command line. So it's all in one place now, very easy. And, okay, time is over, I guess.
It's that time.